Don't worry about it. All right, so we've introduced density a little bit here. Today we'll talk about it in some more detail. So we can define density in several different ways. So what we're going to say is that density is sort of how much matter there is in a given space. How much matter in a given space. How compact the molecules are in a substance. That's what density is. How much mass is in a specific volume. Next page. So density is sort of like a derived measurement of a material. You don't really measure the density directly. You measure the volume, you measure the mass, and then you calculate the density. And one of the important properties of density is that it is what we call an identifying property. And you guess what that means? If I say density is an identifying property, what could that mean? Joey?
Something you can say, this has a certain density.
Yeah. And you can use, if you have an unknown substance, if you find that substance's density, you can use that to help you identify what material it is. Because all pure materials have a certain density. Okay? And that density is pretty much constant. At a given temperature, the density of aluminum is 2.7. So the density of a substance, don't worry about any of the other two for right now, we'll get to those in a second. So this bar of gold and this, oh, that's not my gold. This bar of gold that I hold in my hand, somebody steal my other block of gold. Oh, here it is. No, that's wood.
You had it in your hand earlier.
This is a bar of gold, my super valuable cube of gold, though. Gonna have to go to the video cameras. Oh, here it is. Whew. All right, so this cube of gold and this bar of gold have the same density. Even though they're different sizes, shapes, masses, and volumes, they have the same density because gold has a consistent density. Okay? A gold coin has just as much as a tiny little speck of gold. The density is the same. If I have an aluminum cube and I cut it into 3 pieces, each piece is still going to have a density of 2.7 grams per cubic centimeter. Okay? So if I have some unknown material and I find its density, I can determine what substance it is by comparing that to a chart. Flip ahead in your packet a couple slides to the chart of densities. One more page. It says the density of common materials on the top of the slide. This is a density reference table. And what this table does, you'll be referring back to this various times. It shows you a list of the density of various substances at certain temperatures. So the solids are all shown with their density at 20 degrees Celsius room temperature. Okay, so if you look at that list, osmium is one of the most dense substances on Earth. It has a density of 22.5 grams per cubic centimeter. Okay? Balsa wood is very low density. It has a density of just 0.12 grams per cubic centimeter. And so if you can use this chart to help you identify various materials. Okay? Liquids are on the right, and then you have gases below that. So you can see, obviously the gases, what do their densities look like compared to the other substances? Right? Yeah, much smaller. Gases have very low density. All right. Now, one important factor is that less dense objects will float in more dense liquids or gases. Okay. So, if I have a bar of balsa wood, place it in water, will it float? Yes. Why? Less dense than water. Now you can refer to this chart, but there is one density that you do need to memorize. Water. And what's the density of water? 1 scoop of hummus per pita chip? Gram per cubic centimeter. So anything with a density of less than 1 gram per cubic centimeter will float in water. Anything with a density greater will sink. Anything with an equal density that matches will basically stay wherever you put it. If you put it halfway down a container of water, it'll stay there. Okay? If it has the same density. So if you blow up a balloon with air from your lungs, does it float in the air? No. No. Not unless you have some superpower where your exhalation has a density lower than air. If you fill a balloon with helium from a tank, does it float?
Yes.
Why? Helium has a very low density. If you look on your chart, the density of helium is 0.00178. If you compare that to air, it has a density of 0.00129. What else could you fill a balloon with and have it float? Carter?
Nitrogen.
Nitrogen? Did you say nitrogen or hydrogen?
I said nitrogen.
Okay. Yeah, nitrogen would barely float. Francesca? Hydrogen. Would a balloon filled with hydrogen float well? Yes. Has anyone ever filled a very large balloon with hydrogen? And put people in a little...
Oh, Heisenberg.
Yes. The Hindenburg. Have you heard of the Hindenburg?
Yeah.
It was an airship, like a blimp, but not filled with helium, as a typical modern day airship would be, but it was filled with hydrogen, which is, very low density, so floats very well. Who could tell me the problem filling large balloons with hydrogen? Grady?
It's explosive.
It's explosive, it's extremely reactive and flammable. And what happened to the Hindenburg, Joey?
It crashed.
It crashed and burned, and it was a very tragic situation. But anyway, yes, helium is less dense than air. And finally, although the density of a substance is consistent, if this is pure aluminum, at 20 degrees Celsius, we know its density is 2.7 grams per cubic centimeter. However, temperature does affect density. So that's why this reference chart gives you specific temperatures. Because if this aluminum is not at 20 degrees Celsius, its density is probably slightly different from the given densities in the chart. If I were to heat up a metal object, or any substance, what happens to its volume? If you heat up a substance, what happens to its volume? Aiden?
Like, it would melt and it, like...
Well, before melting, let's say before I get to that point.
Wouldn't it expand? Like, it could reshape and expand,
Yeah, it gets larger. So that's why, if you have a jar that's stuck, you might run it under hot water. What you're looking for is the metal in that jar to expand slightly to make it easier to open. When we heat up a substance, it expands. The molecules spread out. Okay? Because they're moving faster, they spread out. So heating a substance expands it. And so how does that affect its density? If I heat this aluminum block, it will expand slightly. Will its mass change? No, its mass is consistent. Heating it doesn't change its mass. It's not adding molecules to it. So what would happen to its density? Its mass stays the same, but its volume increases. What happens to its density? Right. They get lower. The molecules are not as tightly packed. They've expanded slightly, okay? And its density decreases. This is the principle of how a hot air balloon works. Because in a hot air balloon, you take some air that's in the balloon. As you heat up the air in the balloon, it expands. It becomes less dense than the colder surrounding air, and therefore it floats. Okay? And that's how the principle of hot air balloons works. All right, so as we talk about calculating density, let's just sort of quickly review what we've talked about thus far, volume and mass. Because both of those measurements are required to calculate density. So, what is volume? Give me a definition of volume. Jake? An amount of space that an object takes up. That's what volume is. What about mass? What is our definition of mass? Alex?
The amount of matter inside an object.
Yeah, the amount of matter in an object. So for our purposes of calculating volumes after measuring objects, what were the formulas we used? Tell me the two formulas that would be, Stephanie?
For volume, length times width times height.
Length times width times height, or if it's a cylinder,
Radius squared times height.
times one more thing again. Height. So length times width times height, or pi r squared times height, those are the formulas we use to calculate volume. Do we have any formulas for calculating mass? No, we just measured it. How about the units? I know we all love units so much. What are the units that we use for volume? Dean?
Cubic centimeter cubic, and like a metric thing, cubic.
Okay, you said like 17 different words. Give me your actual answer. What units do we use to measure volume?
Centimeters cubed.
Centimeters cubed. What else?
Meters cubed.
We could if we typically
Millimeters
won't.
cubed.
What?
Millimeters cubed.
Could. How about for as we measure liquids? What units?
Milliliters.
Or
Liters.
yes. So the units we typically use were liters, milliliters, and cubic centimeters. Do we ever cube milliliters?
No.
No. How about mass? What are our typical units that we use for mass? Right?
Grams or kilograms.
Grams, kilograms, what other one? Think vitamins?
Milligrams.
Yes. What kind of equipment did we use when determining volume? Joe?
A ruler.
Ruler if it's something we're measuring. Or Grace?
Water displacement.
Using what equipment?
A graduated cylinder.
Yeah. So either we use a ruler to measure the dimensions and to multiply, or we might use a graduated cylinder for water displacement. How about for mass? Francesca?
A triple beam.
Triple mean balance or digital scale? This is sort of a side note. I meant to talk about this the other day. if you could bring either this digital scale or a triple beam balance to the moon, which would be the one you would use to measure the mass of an object on the moon? Okay,
Triple beam balance?
would that give you the same mass measurement here as it would on the moon?
Yes.
I hear both. I hear yeses and nos. So raise your hand if you think this triple beam balance, if you took that block of gold, you measured it here on Earth, you took the triple beam balance and the identical block of gold to the moon and measured its mass again, would you get the same measurement if you're using a triple beam balance? Who thinks yes? Who thinks no? Okay, who wants to explain? Why do you think no? Why are you giving me a no here? Alex?
Because, like, the planet could affect the triple B balance the same as digital balance could. Like, the digital balance, like, you can't use on there because you need, like, electricity. And the triple B balance would just, like,
Let's say we have battery pack.
Yeah.
Let's take electricity out of the equation here.
Okay.
Okay, Aiden, what do you think? You're giving me no? You're saying it would not give the same answer. Why?
Like, because the electric one, or whatever, because, like, can I explain? Okay, like, the gold bar,
Yes.
you need to take that, like, it changes, the weight changes on, like, a different minute.
Yes.
And with the triple beam balance, the weight changes with it, but like on a scale, like,
I think you're arguing against your answer.
yeah. I'm
You
for
said-
the triple beam balance.
What?
I'm for it because like.
But you just, so I would say, you're saying a triple beam balance would give the same measurement here and on the moon.
Yeah.
Okay. Yes, so that is correct. And yes, your explanation is correct. Because this triple beam balance, because it works using counterweights. So is the force of gravity on the moon different? Yes. So would it be pulling down differently on the golden bar? Yes. But it's also pulling down differently on the counterweights. So yes, if that golden bar was 100 grams here on Earth, and you brought that triple beam balance to the moon, it would still read 100 grams.
Also, the scale would be adjusted for Earth, so,
This scale?
yeah.
Yes. So a scale that's relying on gravity is calibrated to the Earth's gravitational force. And so taking a scale that's just using the pull on the mass of that object would not get the same measurement. All right, anyway, that was second.
but that's electronically programmed, so the surface, since the surface gravities are different, couldn't you just convert them?
You could convert it to mass, but I'm saying the reading on the tool would be different. All right, anyway, that was a side note. Density. Okay, so density. Density is how much matter is squeezed into an object, how compact the molecules are, how much mass there is per volume. Those are all definitions of density. Okay, that's awkward. Everything okay here, Mr. Secretary? Oh, all right, just want to make sure. Oh, okay. I just want to make sure you're okay. All right. That's always interesting. So what formula do we use to calculate the density of an object? Simple formula, 3 variables in it. Taylor?
Density equals mass over volume.
Mass divided by volume. D equals M over V. The units are a unit of mass divided by a unit of volume. Typically, which one are we going to use, Grace?
Centimeters, like, wait, well,
you do like the mass in grams, and then you do the volume in centimeters cubed, or yeah, like, to the third power, whatever that is.
So your answer is trying to discern it in this
Wouldn't you
jumble
measure
of
it
words
in
that are coming out of your mouth. So which units, Grace, would we use to?
grams per centimeter square? Whatever that third three is. Cube.
So Grace, what units are we going to use for density?
Just
Give me
grams
4
per
words.
Grams per centimeter cube.
Good, thank you. Grams per cubic centimeter. Or if we're measuring the density of a liquid, we might have grams per milliliter, but it's the unit that mass was measured in divided by the unit that volume was measured in. Grams per milliliter, grams per cubic centimeter. We don't really use equipment because we use the equipment in finding the mass and volume. You might get a calculator. You will need your calculator definitely when we're calculating density. Okay. So just to reiterate this, the density of a substance is constant at a given temperature. Okay. So if I have these 2 cylinders made of the same material, again, these are the same, would have the same volume, they have the same mass, therefore their density is what? Same. However, if I take this cylinder and I break it into 2 pieces, a smaller piece and a larger piece, how would the density of this piece compare to the density of this piece, considering it's about 2/3 the size? Right?
They would still be the same.
Yep. But let's think about it. You're right. But thinking about it mathematically, I have less of it here. So why isn't its density changing? Francesca?
Because density is like how much, I forgot what the word is, like compacted.
Okay.
So like the molecule is compacted into an object, so like even if you break it, it's still gonna have the same amount of like stuff compacted.
Yes, that is true. But I want to think about it mathematically. So I have, now would this mass be the same as this mass?
No.
No, obviously not. I only have about 2/3 of the material here. So mathematically, why is the number I arrive at, the density, the same? Come on?
Because when the mass lowers, the volume also lowers. So when you divide it, it would still be the same.
So really, density is a what? What would we call that? I thought you were going to say it. Mass to volume, it's a,
Equation?
no, it's a ratio.
Oh.
Right? It's the ratio of the mass to the volume. So in a ratio, if my ratio is 10 to 8, how does that compare to a ratio of 5 to 4? They're the same. The ratio is the same. They've both decreased by half. So even though I have only 2/3 of the mass here, how much of the volume do I have? Also 2/3. I've reduced them both, but the ratio remains the same. So the density is not dependent on how much of the material there is. That's just a long explanation about that. All right. So osmium is actually one of the densest materials on Earth, but it's very rare. Gold, however, is also a very dense and relatively common element that can be taken from the Earth. And so obviously gold was and is used as a form of currency commonly. And one of the reasons gold was used is because of its density, because it's easy to determine if something is actually gold because its density is so much higher than most other metals. And so, if somebody gives you a gold coin, and gives you a coin that's gold in color, but made of some lesser metal, it's gonna be very clear to you which is which. Because the density of gold is so much higher, it's gonna feel obviously different to you. And so, that's one of the reasons gold was used as currency, because people could discern if they're being scammed or not. But what people would do is sometimes take some gold and mix it with some other lesser metal and try to pass it off as pure gold. Okay? And so, how can you determine if somebody gives you, if I were to give you this super valuable golden nugget, how would you determine if it's actually gold or not? Brian?
You could actually do it.
Yeah. I can find the volume of this gold nugget. I can find the mass of this gold nugget, can look at its density, and what should it be? If it is pure gold, what should it be? 19.3
Grams per cubic centimeter.
grams per cubic centimeter. Yes, if I were to calculate the density of a golden nugget that has a mass of 47.9 grams, a volume of 3 cubic centimeters, and I were to use it to buy myself a new suit, and the gentleman, the tailor I was buying my suit from, was checking up on me to see if this gold nugget was actually true, was I scamming him?
Yeah.
Wait,
How do you know? How would you know this? Joey?
Is 19 times 3, it doesn't go into 47.9 evenly?
Okay, it's sort of a roundabout way. If I find the density of this golden nugget by taking the mass, dividing it by the volume, and I look at my result, that's the density of this gold nugget. Is that gold? No.
Part.
Gold is probably part gold. Gold is a density of 19.3 grams per cubic centimeter. All right, any questions about any of this stuff so far? Tomorrow in class, we will talk about calculating the density of various objects and calculating mass if we know density, but that's good for today. No homework.